So I think it's very ambitious title. We really look forward to your talks. And Martin shared his slides. There are 5 slides. Some are bonus slides, and some slides Martin will use here. So you don't have to make screenshots or anything. It's all shared. It's on the back. So please.
Okay, thank you, Tom, and thank you for the invitation to be here. It's a pleasure. Before I start, well, first of all, let me repeat that indeed, I mean, feel free to ask questions whenever they come up. So don't wait until never to ask them. Also, the lecture will be structured in 4 parts. So we can take sort of a short breathing break in between. And the other thing I'd like to ask is a bit about your backgrounds. Unfortunately, I missed the speed dating yesterday because I needed to finish some of the slides here. So are there people who already know something about meteorology, weather and climate? There's 2 in the back and a few people who at least have seen a cloud outside.
The profession is climate science. The profession is...
Yeah, right. And how about your backgrounds in terms of supercomputing and modeling and those kind of things? Not so much. Okay. And how about your backgrounds in machine learning? So there are also a few here. So, okay. So it looks like most of the stuff I'm going to present you is really new for you. So let's see if I find the right sort of balance in terms of getting into the depth and ugly bits of pieces, and just giving you a general introduction of how these things work. So let me start with some facts about weather and climate. And it's my very strong belief that if you do want on the subject, you need to know certain facts about systems in order to actually achieve meaningful results in the end. And let's start very simple. And so in this first part of the lecture, there's a bit how weather is created. I will show you a glimpse of the governing equations of large-scale weather. Tell you a little bit about the added complexity of air pollution. This is not really the main focus of these lectures, but just to give you, again, a hint what's in it. And finally, this goes a bit more, I think, into the main topics of the summer school, some information about how weather is observed and what kind of data you're actually finding if you want to work with weather data. So let's start very simple. We all know that the Earth is rotating around the sun, and this already has a couple of implications on weather, because basically there's different angles by which the sun illuminates the Earth, and also the distance to the sun varies slightly, and due to the rotation, due to the tilt of the axis and the rotation of the planet around itself, you will introduce cycles. And so there are a couple of cycles eminent in the weather and climate system, which are important. Of course, the easiest ones are the annual cycle, so the rotation of the Earth around the sun. We do then see the seasonal and latitudinal dependence of solar irradiation, very obvious. So these days we can walk around with t-shirts. In the winter, you want to wear a warm jacket in these latitudes. We have the 24-hour daily cycle. But then we have a couple other cycles here that are important on the climate time scale. So the eccentricity of the rotation varies on cycles of about 100,000 and 400,000 years. We have the obliquity that also changes. So you see in the sketches here, basically the expansion of this ellipsoid. The eccentricity, the obliquity is the tilt of the axis of the Earth, of the rotation axis, and we have a bit of a precession of this axis, and that leads to about cycles of 19,000, 23,000 years. On top of that, we also have something that's happening on the sun, that's the sunspot cycles, which vary with a frequency of about 11 years. And all of these induce some signals in the climate system. And some of these you can really find, for example, in ice core records. So here's a famous paper, Nature 2001, where they could actually show very clearly some peaks in the power spectrum, basically really related to these, basically, if you like, geometrical features that I just showed to you. So that's the first thing that influences weather. The second thing is radiation and the reflection or absorption of radiation. You probably have seen this famous Planck curve down here, which shows you how much radiation is emitted by a black body depending on the temperature and the wavelength. So well, depending on the wavelengths, but for different temperatures, you see these different Planck radiation curves at a temperature of around 6,000 Kelvin. So this is the surface temperature of the sun. You can see that the peak is actually in the visible spectrum, but then you have a very long tail to long wavelengths. Now, this is the curve for a black body. And if you've ever seen images, for example, from the space station, you know that the Earth is not a black body, but looks quite different. And if you want to form this in theory, you can basically go through steps of making the theory a bit more complicated. So the first one is moving from a black surface, the total absorption of a black body, to a gray body, which has a certain amount of reflectivity. The next aspect is to actually add the continents and water, which have different properties in terms of heat capacity, but also, of course, albedo, so the amount of radiation that's reflected back into space. And then the final step is to add the atmosphere, where you find gases which absorb and reflect, but also, of course, the clouds. And clouds do have a pretty strong influence on the radiation budget. These absorptions in the atmosphere lead to this, if you like, change of the ideal Planck curve. So the yellow curve shows you the sunlight at the top of the atmosphere, which is still following the Planck curve for the most part. And then if you measure radiation at the bottom, at the Earth's surface, you will find this red zigzag curve here. And you can see that there are several areas that are sort of blended out of the yellow curve. So it starts here with the UV. And this is the famous ozone layer in the stratosphere that eats away the most shortwave bits of radiation, so that we are shielded from the harmful UV radiation. And then you see all these kind of peaks going in here, and these are absorption bands of various molecules in the atmosphere. For example, also CO2, which is, of course, the main driver of the greenhouse effect. You can then estimate, basically, partly through model simulations, the radiation budget of the atmosphere. So you see incoming solar radiation, mostly in this visible UV, slight infrared spectrum. And you can see sort of what happens to the sunlight. So a bit of that is scattered back into space already in the upper atmosphere. Then you have reflection by clouds, you have reflection by the surface, you have absorption by ocean and land. That's about half of the incoming light. And you have absorption by air, water vapor, ozone clouds, and dust. And the radiation that's absorbed will sort of heat up the system, so the atmosphere or the land. And then if bodies heat up, they will re-emit radiation in the infrared spectrum. So this is the long wave radiation. And so there you basically get this emission from the surface in the form of conduction and latent heat, but also just long wave radiation as such. And again, you will have some absorption. This is actually the greenhouse effect. And then some of that radiation is also again radiated back into space.
This is an average for the whole planet. I mean,
this is the average for the whole planet, of course.
Can have a different percentage.
Yeah, right. And locally, of course, that changes dramatically then. And just two numbers that I haven't written down here anywhere, but you get about 1,000 watts per square meter as incoming solar radiation. And if you look at the typical greenhouse gas effect, we are talking about numbers that are on the order of 2 to 3 watts per square meter. So that's a tiny number in comparison to the incoming radiation. Yet, due to this complex feedbacks here, this is really what drives the change of a few Kelvin per century or so. So that's just
and our use of energy on the human use of energy on the planet probably is a little fraction of the solar energy we get, right?
It is, right, yeah. But still,
look at the numbers, it's scary.
Yeah. Okay, let's move on. So this is, in a nutshell, basically the main processes that drive weather. Of course, there are other effects happening here, like the rotation of the Earth that induces, of course, some momentum. Also, then the Coriolis force that drives sort of weather systems away from the equator. Then, of course, you have physical processes and all that, but I don't want to go into detail there. Let's briefly look into a bit of mathematics. And there, the governing equations of the atmosphere are primarily the momentum equation. So it's basically Newton's second law of motion. So if you exert a force on a body, it will move with an acceleration that's proportional to the mass and the force. And this, for the atmosphere or for fluids, this actually then translates into the Navier-Stokes equation. The other equations that are of relevance for the atmosphere, but I won't go into detail here, are the thermodynamic energy equation. So basically what happens in terms of heating and cooling. The continuity equation for total mass. So basically we cannot lose or gain mass in the atmosphere. It's not entirely true because there is a tiny loss of molecules into space, but it's really a small fraction. And this also holds for example, water and trace gases. So of course you can convert water from the gas phase into the liquid phase or particle phase, ice clouds, but the total mass of water will remain unless of course you evaporate or urine. And then finally the ideal gas law, which basically governs the relation between temperature, pressure, and mass. Okay, so let's go to a little bit into Navier-Stokes. So the Navier-Stokes equation describes the motion of viscous fluids. And so it begins with the conservation of momentum, shown here. So you get the momentum of the flow field. It's basically the time gradient and the spatial gradient. And this consists of two terms, the viscous stress and the acceleration forces. On top of that, you add the conservation of mass, shown down there. So again, there's basically the change of density in time, plus the basically incoming and outcoming mass has to be 0. So that has to be conserved. And if you put that together, making a couple of assumptions, first assumption is linearity, the Galilean invariance of stress and isotropic fluid. And then you decompose the stress into an isotropic stress and the deviatoric parts. And then you eventually arrive at the actual equation of state. And this is the Navier-Stokes momentum equation that's shown here. So you get this acceleration of the flow field, the different stress terms, and the acceleration forces at the end. Now, in reality, the viscosity may depend actually on the temperature and the pressure, as well as on the actual process. And one example here is the frequency of sound wave. So I'm really only showing this to you in order to point out that the atmosphere is quite complex, even just in terms of the fundamental physics that's underlying the atmosphere.
This formula applies only to fluids.
This applies to fluids, yeah.
So let's say if you have a 1 cubic meter of fluid, like an oxel, and then you can apply this. And so what is the volumetric stress? What is it exactly?
Volumetric stress is really the basically force by expansion and shrinking.
Okay.
Yeah. Right. So to make things even more complicated, we have to regard the geometry of a sphere. So the equation that I showed you before is basically for, just as you said, like a box in the Euclidean space, but the Earth atmosphere is a sphere. And then if you want to translate these equations onto spherical coordinates, this is roughly what you arrive at. And this is actually now copied from Okay, unmute. And where is it? No, that's the, I thought I had the presentation mode. That's just, that's the entire screen. Okay, we can do that. Yeah. Okay.
Yes.
So am I back?
Muted?
I'm still muted?
Just asking.
No?
Can check. Yeah, perfect.
Yeah, should be okay now. Okay. Right, so let's move on. We leave weather behind for a second and take a glimpse into, okay, to make sure that I'm, oops, now here, the right one. Okay, take a glimpse into air quality, which adds yet a bit more of complexity to the system. So this is actually a scene of Delhi, a very nice place to be, except for the air quality. So sources of air pollution are several. So we have fossil fuel combustion, we have the combustion of biofuels, degassing and fugitive emissions, abrasion, physical lifting, and also natural biochemical or geological processes. So there are some examples shown in these photographs here. And so these different processes, of course, act differently. And to relate this a bit to data or geoscience, of course, you will find, let's say, aspects of this if you look, for example, at land cover maps and stuff like that. So the distribution where these different sources are, which kind of landscapes could lead to emissions of these different substances. So that's actually, I think, a very nice linkage between geoscience and also geoinformatics with, for example, air pollution research. And that's, in fact, how Ben and I got together in a way. Okay, now what happens then in atmospheric chemistry? You have emissions as sort of the driver that puts stuff into the atmosphere. And then you have chemical processes that will convert different pollutants into each other. You can transport the air pollution. So obviously, you can see that very clearly here in North Rhine-Westphalia, if you have these big coal-fired power plants and you just observe the plumes from these power plants, that they will distribute the stuff somewhere. Then you have phase conversion, so gases can be attached to particles or can convert, can lump together and form particles, for example, or particles can re-evaporate and form gases. And then eventually you will have something like deposition, where stuff in the atmosphere will deposit on the ground, which can actually also lead to damage. For example, buildings can be affected by air pollution. So you might know these old Romantic or Gothic cathedrals, which often have these black looking stones, and that's actually from air pollution, so weathering. And then if you look a little bit into what kind of drivers influence these different processes here, you will find different driving factors like human activity, especially for combustion processes, of course. Then some meteorological factors like the temperature. So chemical reactions, these chemical processes depend on temperature. Also solar radiation. So some of these air pollutant molecules can be photodissociated. So if you have sunlight shining onto the molecules, they will dissociate and form two radicals, which then react with other stuff again. Wind speed, of course, drives the transport of these substances, also vertical mixing. So people in Germany might have heard about Stuttgart, for example, that lies in a valley. And so in winter time, when there's these inversion systems, the air is kept in the valley. And so this is why aerosol pollution accumulates and accumulates and accumulates. And you get pretty bad air quality in the city then. Humidity is a factor. And then finally, things like surface characteristics, for example, also for the deposition processes. This is important, again, sort of with a glimpse into the future, what we are going to discuss here, the machine learning on weather, air pollution, and climate, in the sense that by knowing these kind of dependencies, you can kind of get an idea what kind of data you actually need to input into your machine learning processes in order to make meaningful predictions or analysis of the air pollution, in this case, air pollution system. And to look at that from an equation point of view again, so this is the primary equation that's of relevance for air pollution is the mass conservation. And here on the left side, upper left, you see again the different form of the, let's say, general equation of mass. So the temporal change and the spatial change, if you like, the transport change. And then on the right-hand side, you add all these different terms that basically describe all these different chemical processes, including deposition, washout, emissions, chemical conversions, and so on and so on. So that's in a formal manner, basically how you describe the air pollution in the atmosphere. Any questions to that? Nope. Okay, then let's move on. How do we observe weather and also air pollution? And what kind of data do we get from this observation system? So this cartoon already shows you in a glimpse, basically, the different types of observation systems that we have around the world. So there are ground-based stations, there are balloons, stratospheric balloons, there's aircraft, gliders, there are satellites on the top, there are some ships equipped with measurements, there are aircraft, yeah, I said that already, I think, radar stations and other stuff. And to go through a couple of them, these are snapshots from different data providers or also data collectors, basically. So for weather, the let's say key or core organization is the World Meteorological Organization. They are in Geneva, and they are basically maintaining a big archive, or it's actually a federated archive distributed into regions. So they're regional data centers that collect the different observations. And so from surface station observations, they have about 100,000 active sites around the world. So it's quite a number. But you can also see that the coverage is reasonably good for the continents, of course, but you can also see there's still quite a couple of gaps, for example, in the Sahara, in the northern Canada, and so on. And of course, the oceans have much less coverage of surface sites than continents. There's another viewpoint on surface stations here from a climate analysis center, basically, where you can also see the temporal coverage, so when these sites started. And so if you want to go back for climate analysis to the, let's say, very early days of weather observations, around 1800 or so, then most of that is really concentrated over Europe, a bit on the east coast of the US. And then during the, let's say, late 19th, early 20th century, the number of stations became much larger. But then only after about 1960 or so, you got much more coverage now also in the rest of the world. So there's clearly an imbalance, and this, of course, can be a factor if you want to do climate analysis, because your data will be inconsistent to some extent with respect to global coverage. Next type of data, and I apologize for the quality of the view graph. This is taken from the WMO website. They should produce a better quality one. They have about 1,300 radio sonding stations, and here every day, basically, there's 1 or 2 balloons that are launched into the atmosphere and then measure the vertical profiles of temperature and pressure and wind.
And it's always the same locations.
They're always the same locations, yeah.
Okay. And then these balloons, they pull them down, or
they're not tethered, so they will come down eventually, and usually it's kind of a styrofoam box, and which has like a sticker on it where people should send it back if they find it. But of course, you can imagine if they fly in, for example, the Amazon or so, that most of these things would just be lost.
okay.
And then finally, for better coverage over the oceans, there's also a buoy system. There are about 1,200 of these drifting buoys. So they're not tethered to the ground of the ocean or something, but they're just floating around. And so you basically need to take into account the motion of these things. And of course, by tracking the motion, you can also learn something about the ocean currents. Right. Then we have aircraft. Civil aircraft, there's a subset of all the airliners basically are equipped with so-called AMDAR observations. So they also measure, basically every aircraft measures temperature and pressure and wind again. But there's a subset of them that send this data in real time to some receiving stations on the ground. And this was actually an effect that was measurable during the COVID pandemics when many aircraft were grounded. That the quality of the weather observations was markedly decreased. So there was somewhat worse weather forecast during that time due to the fact that a lot of this data was missing. Again, you can see that there's quite a bit of a bias here towards the Northern Hemisphere and far less aircraft covering the Southern Hemisphere. And then finally, we have satellites, a constellation of different instruments constantly being improved and changing. So for Europe, we have these Meteosat satellites from EUMETSAT. We have satellites from India, Russia, China, again, South Korea, Japan, and then, of course, the US. And these satellites are basically, there's different types. So we have these polar orbiters that somehow circle around the Earth, and polar orbiter because they will cross the poles on their track. So there you always get a snapshot, of course, of the Earth or the weather system for a couple of minutes, basically, depending on the exact orbits, up to 2 or 3 times a day. And then you have the geostationary satellites located around 40,000 kilometers above the planet. And they will be around the equator, and they will always observe the same spots, so you can get a much better time resolution. But of course, since they're much further away, your spatial resolution will be worse. Okay, and now in practice, if you want to work, for example, with satellite data, there's a couple of nice viewers available and where you can also download data from. So for European satellites, EUMETSAT has this EUMETView tool. For example, you can sort of interactively select data here and visualize it directly, or you can access an API, which has then these open geospatial consortium services. So web mapping service, a feature service, or a coverage service, which you can use to extract data from the system. Similarly, for NOAA, which governs the weather satellite data of the United States. You have this GOES image viewer, where again you have the different fields basically that you can select and then superimpose on the surface. And there's also some way of downloading the data. I forgot the details now, how it works exactly. So here's just one example for example, a 6.9 micrometer. So this is in the infrared, mid-level water vapor. And this is just to show again that also these observations have very peculiar characteristics, which are important to understand if you want to work with these data. So naively, you would think that a satellite observing clouds would just sort of see white surfaces or something like this, and that's a cloud. But of course, clouds vary with altitude, they vary with density, and so on and so on. And different channels, so different spectral channels of the satellite will observe this or different aspects of the atmosphere. And so in this mid-infrared range, you will actually see clouds at altitudes around sort of 5 kilometers. Primarily, that doesn't mean that they're exclusively on the system, but this is sort of what they that you primarily observe with this channel. And this gives you a little bit of a glimpse in terms of for ESA, another European space agency. So they have this climate data search interface. So EUMETSAT is more focusing on weather observations. ESA has a bit more of a focus on climate. I've actually seen yesterday, I think in Tom's presentation already, the CCI data that you've been using also. So that's the climate change initiative from ESA. And you can just see several variables here that are observed from space. So from aerosols, clouds, greenhouse gases, ozone, ocean color, sea ice, sea level, and so on and so on. So there's quite a bit of information about the state of the atmosphere, but also the land surface that can be observed from satellites.
And all these are like the solutions, I don't know, 20 kilometer, 25 kilometer or something.
It's very different. So, I mean, these kind of typical atmospheric observations, like clouds or so, typically are on a resolution of, say, 1 to 5 kilometers. That's typically what you get.
Okay. And is it also a lot modis-based, or
Sorry?
are they modis-based, the products they make, or they're purely from the European?
No, I mean, all kinds of different satellites. So for the atmosphere, there's actually, I think, more variety. I mean, I've come to know that for land surfaces, you usually have things like MODIS and Landsat and maybe Sentinel now. But for weather systems, there's a lot more there in terms of different satellites and instruments that are used. All right, and then also ESA has this kind of CEDA archive that you can use to extract data. So you can download files here, you get all the metadata about the products. Yeah. One more aspect is a bit about the geometry. I've briefly told you about polar orbiters. So this would be sort of a composite of different flight tracks and what is observed on these flight tracks. And you can see these kind of weird looking stripes here covering the map of the Earth. And this is a kind of viewing geometry, or let's say image geometry, you need to live with if you want to analyze or use this kind of data also in machine learning. And you can immediately imagine that in order to really make something meaningful out of that, you will have to work on things like imputation, so filling the gaps, or somehow find other ways of dealing with all the gaps in between these observations here. Yeah, similar things also shown here in a bit more detail, and you can see so that you have simply due to the projection now. I mean, of course, the actual satellite will always observe the same width along its flight track, but if you project that on the map, you might end up with these kind of funny geometries that you have to work with. Right.
These shapes like continuously in time, or do they change like after a week? They get shifted in the place which the satellite covers?
No, usually they're on a constant flight track. So basically you will get a repetition cycle then. It depends on the satellite. So some, I mean, you have different viewing geometries. Some have wider swath and others have narrower swath. So sometimes you will have an overlap so that, I forgot which satellite now exactly, but I mean, there are some that will basically cover the surface every 2 days roughly. And then you might have an overlap that you see the same scene or parts of the same scene every day. Others you might need like 16 days or so before they've covered the entire surface and so on. That's very different. Okay, a little bit about data formats. So how to work with this kind of satellite data, and the format that's mostly used these days is HDF5. Who knows already the HDF5 format, has worked with it? So that's a couple people. So just in a nutshell, some main aspects of HDF5 are that it's a high performance data software library. So this is, I think, one of the reasons why it's so popular, because satellite data can be massive. So just for information, ECMWF processes about 120 terabytes of satellite data every day that goes in their weather forecast. So that's quite a number. Also, it allows you to store heterogeneous data, and looking at the tracks that I just showed you, this is quite heterogeneous in format, and it's really built for fast I/O processing and storage. Another big advantage of the library is that it's architectural independent, so it runs on a wide range of computing platforms and operating systems. You have interfaces to several different programming languages. I would imagine that also Julia belongs to it by now. And you have some advanced performance features that allow you for optimizations of the access time and storage space, where you can even plug in your own compression or packaging routines into the library. Yeah, so these are several aspects. I mean, this is a bit of a branding here. Again, summarizing the advantages of the HDF5 format. Let's skip that for now and just show you a couple of concept examples. So a file is also called a container in HDF5, and that can also be a group. So you can basically have several of these boxes stacked together into a file if you have several groups. And a group then consists of folders and objects, which are the data sets. So you can package different stuff together. And then a data set itself consists of data and metadata. So you always have the metadata together with the data, which makes this format a sort of self-describing data format. So you don't need to download numbers and then search somewhere for the metadata describing these numbers, but it's all together in one file. And here's a bit of a glimpse on the different storage facilities, how you can do that. So the first one, the default is a continuous storage, where a field is really just saved in one block, where basically the data elements are stored physically adjacent to each other. But you can also select a chunked system, which allows you to have faster access to subsets if you kind of know your access patterns. So people will always extract, for example, data over Europe or something like this. You can define your chunks in a way that you can get much faster access and process this in parallel also. And furthermore, you can also then compress these chunks so that they take up a lot less space on the disk system. The other file format I'd like to briefly mention is netcdf, so the network common data format. Actually, by now they have the same engine under the hood, so HDF5 and netcdf share the same sort of fundamental library. But netcdf has a somewhat simpler data model, so you can also define groups, but you don't have this thing of having folders and different data sets inside a group, but basically groups always share the same attributes and dimensions. And so you always only have a set of variables inside a group, which then need to have the same dimensionality, basically. Now a bit on how to work with surface observations. So again, there are various systems available where you can access, for example, climate data online from NOAA, where you have different tools available, like a search tool, a mapping tool, and data tools to access the data. The Copernicus Climate Data Store from ECMWF is also a nice resource for all kinds of data sets. You also have a toolbox there that you can use to visualize data. There's an API to access and extract data. And indeed, you can also get help from the support portal. And this is just a snapshot here. So a couple of data sets for seasonal reforecast, for example, for river discharge or near surface meteorological variables from a bias corrected reanalysis and all kinds of stuff. Point is once more that it's useful to have a bit of an understanding of the weather system, but also what these kind of different terms mean. Like, for example, what is a reanalysis? Yeah, so I'm not going into details here, but basically this means that in general weather forecast, you will have updates in the weather model and the data assimilation system every 3 months or so, which means that if you paste together a time series from operational weather forecast, you might find some disruptions in this time series due to change of the system. In a reanalysis, you will use the same model, a sort of frozen model version, and rerun all the data assimilation and forecasting for a long period. So it gives you much more consistency. It doesn't mean that it's 100% consistent, because there's still changes in the observation system itself. So satellites come and go, for example, and that also has an influence on the performance of the model. But it's much more consistent than just pasting together chunks from the operational weather forecast. So that's just one little thing that's useful to know if you are planning to work with that kind of data. And finally, for air quality observations, I can just recommend our own data infrastructure that we built at the JSC in Jülich, the TOR data infrastructure. TOR stands for Tropospheric Ozone Assessment Report. As the name suggests, it's focusing more on gas phase species like ozone, but also precursor species. If you want to look more for aerosol observations, there's other data centers there. And in this data center, we don't have a graphical web interface yet for the new system, but there's a REST API, there's lots of documentation. And we are building currently an analysis service that you can directly process the hourly observations and calculate aggregates, for example, online on the fly. Okay, now to end this first part, a final word on scales in the atmosphere. Because that's, of course, also relevant if you're looking at building machine learning applications for this kind of system. And that's, I think, one of the peculiarities of, well, the Earth system in general, but specifically also the atmosphere, that really spans many, what's it called again? Many powers, basically, in the scales. So in the characteristic length scale shown here on the y-axis, it goes from like centimeters to thousands of kilometers. You can see the different phenomena there, from microturbulence, boundary layer turbulence, cumulus convection, thunderstorms, cloud clusters, cyclones, and planetary waves. And these are related kind of obviously to time scales from seconds to centuries, really. So that basically, I mean, microturbulence, for example, is really fast process happening on a centimeter time scale within seconds. And then on the other hand, you will see at the typical resolution of current weather models between somewhere 1 kilometer and 10 kilometers, you will find thunderstorms or sound waves. So that's basically then determining what can be resolved in these models. We'll come back to that later. Okay, any questions to part one?
Boundary layer turbulence, is this from the flight path of the satellites, or?
No, I mean, the boundary layer is really the lowest layer of the atmosphere near the surface. Yeah, and then you get basically mixing within this boundary layer. So in summertime, you can reach up to 2 or 3 kilometers. And then you have basically eddies turning around the air inside this layer, basically, of the atmosphere. Okay, then with that, we all take a big breath a couple of times, and we will move on to part two. Okay. The drink is something nice. I'll also just have a glass of water. So how are we doing on time, Valentina?
Yeah, it's 15 minutes.
Okay, very good. Okay, are you ready to absorb some more? Good. So now we will go a step deeper into things that are relevant for machine learning. And this is some discussion of the statistical and technical properties of environmental, specifically atmospheric data. So let me begin with a nice quote from a book that I will present to you in a minute also. Underlying both descriptive and inferential statistics is the notion of uncertainty. If atmospheric processes were constant or strictly periodic, so coming back to what I showed you at the very beginning, describing them mathematically would be easy. Weather forecasting would also be easy, and meteorology would be boring. So I guess we are lucky that the system is so complex and we still have things that we need to figure out and discover. So what I would like to present you in this lecture are a couple of aspects. Some of them might be well known to you, others maybe not so. I'm highlighting things that are, let's say, not so common in the classical machine learning theory. So that's basically why I'm presenting these things. Starting with non-Gaussian statistics, evaluating forecasts of discrete events, evaluating forecasts of continuous variables, a word about autocorrelation, and then some special issues related to weather and climate variables. Or actually, I moved the atmospheric length and timescales. You've seen them already. Yeah, should remove that in the content slide here. And this is a book that I would actually highly recommend if you're more interested in really working with weather, climate data. Daniel Wilkes, Statistical Methods in the Atmospheric Sciences. So this is a really good coverage of what's going on and how you deal with statistics in atmospheric science. So let me first tell you a little bit about non-Gaussian statistics, because in particular, if you talk to machine learners, they very often have it already almost burnt into their brains that everything is Gaussian. And not only machine learners, but many other scientists during their career tend to more and more believe that statistics means Gaussian statistics. And that's, of course, completely wrong. So just to recapitulate, there are other things that are well known. For example, the Poisson distribution of rare events. But it's important to go back and think a little bit about under which conditions are these kind of distributions actually meaningful. So what do they describe? And so the Poisson statistics really requires that events are independent, also that they're seldom enough, that the likelihood of a concurrence is very small, so that not two of these events will occur at the same time. And third, very important, the probability of these events remain constant over time. And if these conditions are met, you can actually use that formula here. So an expectation value mu to the power of x, e to the power of minus mu over x faculty, basically then gives you the probability of the event x to occur. In practice, this can be used, for example, for tornado statistics in the US. So this is a pretty old example from data from, you can see here, 1969 to 1988. You see these numbers, they're very small. So it's 1 to 6 tornadoes, or 1 to 9, actually, 9 is the maximum here. And then if you just simply apply that Poisson formula, you would get these probabilities for observing 0, 1, 2, and so on tornadoes in the year. You can see peaks at around 4 tornadoes. And if you look at the table, that's roughly what you would see. Indeed, if you plot the data and the expected values, they kind of match and overlay. But you can also see, of course, that there's a lot of noise and deviations between the expected value and the real occurrence. So that's basically just to let's say recapitulate a bit of a glimpse of really very basic statistics, but make you aware again of how to think about statistics and how to apply basically statistical methods.
Log normal distribution.
This is not log normal. This is a Poisson distribution.
Okay.
See, you're also biased towards Gaussian stuff.
I see. Kind of goes up on the edge.
Yeah. But there are differences. And this is just an overview of typical distributions that you can find in atmospheric variables. So of course, we also do find processes that follow the Gaussian distribution in the atmosphere. But then there's also your log normal distribution. There's a gamma distribution, exponential distribution, chi-square distribution, person, beta, generalized extreme value distributions, and so on. So all of these play some relevance or have some relevance with respect to atmospheric processes. And the main thing is that indeed, I mean, you do have different expectation values and of course different behavior primarily with respect to the extremes. So for example, some of these distributions are clearly asymmetric. That's very important to consider. Or you will find, in particular, if you're interested in extreme values, of course, very different behavior in the tails of these distributions. And it's kind of obvious. I mean, people living in Germany know this, that last year in July, we had these tremendous floods in the R Valley and so on. Right now, they're occurring in Pakistan, for example, and these are extreme events, and it's kind of important because they really cause most of the damage from weather-related damage, to be able to capture them, let's say, reasonably well. So yeah, one I think pretty important example for these distributions is the gamma distribution. Just to show you that it depends on the so-called shape parameter alpha. So you can have the larger alpha gets, the more this gamma distribution actually resembles a Gaussian distribution. It also flattens. But you can see that through this alpha parameter, you can also do something that looks much more like an exponential distribution. And this kind of distribution is typical for actually quite a few variables. If you think, again, for example, on air pollution, then you have concentrations of trace gases or concentrations of aerosols. And obviously, we cannot have negative concentrations, which means these distributions have to be zero bound. Yeah, and so a Gaussian distribution would not give you that. Yeah, so but the gamma distribution, you can use that to describe this kind of these kind of variables. And again, it's kind of important then to understand that basically to what extent a machine learning method actually makes implicit assumptions about the underlying distribution of variables. This is just one example how you can actually make use of the shape parameter of the gamma distribution. So here they've then basically plotted a map of January precipitation. So basically for every location, they fitted a gamma distribution to it and then sort of plot the shape parameter on this map. And as you could just see before, so here towards the east, you will see larger values. So meaning this looks a bit more Gaussian-like. And here towards the west or southwest, the shape parameters are much smaller, so you have much more, very many events with very little precipitation, and then a few with a lot of precipitation. So this can be used to sort of characterize the weather system. And then one other thing is the generalized extreme value distribution, which is used for statistics of extreme events. And here, the main point I want to make is I don't want to really go into the formula, how it's derived and stuff like that. But again, it's sort of the requisites to actually use this kind of formula. And again, you need to be reasonably sure that the events are independent, that you have a sufficient number of samples, and that the extreme events are drawn from the same distribution so that you don't have, let's say, very different conditions which lead to different distributions, and you sample one extreme event from one distribution and the other one from another one. But it's really the same underlying processes, basically, that determine the distribution of extreme events. Marcus.
These statistics, they are algorithmic, or do they have an underlying argument?
There's an underlying, basically, mathematical derivation of them. I mean, honestly, I don't know all the details, how it was derived. I read it, but I forgot it again, so.
I can read it and forget it.
Yeah. Right. Main point is, again, and this is something I guess to be very much aware of. There's a nice example, which I didn't bring now, but one, let's say, cardinal error that's often observed if you look at data scientists analyzing weather data, and they want to focus on extreme events, is that they only pick the data of the extremes. So, for example, you would want to analyze, say, storms, and then you make a data selection, and you only consider episodes that have wind velocities larger than, say, whatever, 30 meters per second. Well, that's exactly the way how you should not do it, because you're basically skewing your distribution, and you're biasing basically your results towards the extreme events. So it's always important to consider the entire distribution and then sort of use this kind of extreme value theory to basically extract the portion of extreme events from it and work on the extreme events. Yeah.
Air like events are independent.
Mhm.
I'm not sure I'm following like how an event is defined, like is it spatially independent or I'm not sure what an event
Okay, it could be something like, for example, heavy precipitation. And now an easy example would be if you have, say, 2 measurements with 1 hour distance. Yeah, and then you have a heavy precipitation events and you measure again an hour later, you can be reasonably sure that they're not independent because it's still the same precipitation system. Yeah, so that's a simple example. Okay, another aspect, and that's also frequently occurring, for example, in the case of rain or no rain, is the evaluating forecast of discrete events. And so typically what people do then is to set up these contingency tables, where basically you compare observations and models. So model normally in the classical sense would be a numerical model solving all these differential equations that I showed you before. But it can also be, for example, a machine learning model. And so you basically define these 4 quadrants. So a correct forecast would either be if the model is true and the observation is true, or if the model says it's false and the observation also says it's false. So let's assume both would say no rain or both would say rain. And then, of course, you have 2 erroneous boxes here when either the model says it should rain, but the observation says no, it's dry, or the other way around. And then there, you can basically, almost like in combinatorial theory, you can combine all these different boxes in various ways and define different scores and ratios that are used then to evaluate these forecasts. So the, let's say, simple thing, so if I were to give you, let's say, a group exercise and ask you to figure out what would you use to evaluate the forecast, probably most of you would come up with this proportion correct. So you would just say, okay, let's evaluate that by just adding together the true forecasts and dividing that by the total number of events, and that should give me a reasonable assessment of the quality of my forecast. Well, as I will show you, that's not the best way to proceed. There are other things like the hit rate, which basically you're only looking at the true forecasted events. So let's stick to the rain example. It rained, and then we want to see basically rain versus the total number of true observations. So the how many of the true observations were captured correctly. That doesn't say anything about the false observations then, of course. The other thing that's quite relevant is the so-called false alarm ratio, where basically the model would say false. Let's see. Oh, right, no, sorry. The observations are false, and you divide that by all the true model forecasts. So basically how often the model errs with respect to saying it's wrong, but it could be true, but in the effect it's a wrong observation or false observation, and so on and so on. And then there's one extra thing written down here, which is a bit more complicated to derive, but still, if you read in the Wilks book, you will be able to understand that. There's one aspect here that these ratios up there are basically, let's say, absolute in the sense that you cannot tell how far they differ, whether they're significant in a way, so whether they differ from a chance or random forecast. And there's this Heidke skill score, which takes that explicitly. So basically, yeah, it sort of measures to what extent the model is beyond a random forecast. We can play that through with some numbers. So if we had more time, I would ask you to actually evaluate these things. So here's an example, and that's kind of typical for what you might get, what you might find if you evaluate, in this case, a total of roughly 350 or so. Right, 365, I remember. I made it for like daily forecasts. So if you had like a 365 forecasts, and you would have 92 of them would be correct and true, 217 of them would be correct and false, 11 would be where the model says true, but actually it did not occur the event, and 45 would be the other way around, where the model would say no, but the observations actually said yes. And just by sort of pondering about these numbers a little bit, you can observe that yes, I mean, the let's say true and false boxes are not too far away. I mean, a factor of 2 or so, but that's still okay. And typically you have many more good forecasts than bad forecasts. And if you plug in the numbers, this is what you would get. So the proportion correct would be 85%. In this case, it's a meaningful number. In particular, one value, I didn't explain that to you before, the threat score, 0.62, shows you that this is a, let's say, reasonable forecast. But of course, it's clearly away from 1. So in an ideal case, this threat score, so it's again, basically looking at the true model results over true and false model results versus true and false observations. And right, so in an ideal case, if you had zeros in the 2 red boxes, of course this ratio would be 1. But in reality, you're typically far away from 1. So 0.62 is actually not bad. Okay, let's do another example. So here again, we have we have fewer observations now. And we see there's only 3 events where both the model and the observations were true, 257 cases where both are wrong, and then 5 forecasts where the model said it's true, but actually it was not true, and 1 where it's the other way around. And this is kind of typical what you might see in precipitation forecasting, for example, because rain is actually relatively rare. I mean, this summer we can clearly see that here, but also generally it's you always annoyed when you have to take out your umbrella and you think it's raining all the time. But if you look at the statistics over the years, there's actually relatively little rain, or relatively seldom rain occurring. And in this case, if you evaluate all these scores again, we will find that, for example, this proportion correct indicates 0.977. So it would be an almost perfect proportion. And so a naive data scientist would think, well, that's great. So I have a wonderful forecast. But if you look at this, I mean, there's clearly many more, or almost twice as many wrong model forecasts as correct model forecasts for the event occurring, which basically tells you it's not really a meaningful forecast. So the proportion correct is not a good measure. On the other hand, you see that the threat score clearly has a much lower value than in the example before. So this is kind of a useful number. And then again, also this Heidke skill score may be useful. Okay, so that really was just to give you a glimpse. I mean, of course, that would require more time to really get familiar with all these different metrics here, but it's kind of very important to keep that in mind. That evaluating forecasts, in particular in terms of discrete events, so whether they happen or not, is really not trivial. Just a note, you can also expand this kind of system, so you can also build up contingency tables of more than 2 states. So for example, if you bin things into certain threshold values, and then always look at whether things are larger than, for example, wind speed larger than 10 meter or 20 meter per second or whatnot. And then you can apply similar evaluations. Evaluating continuous forecasts or forecasts of continuous variables. There's the famous MSE, mean square error. That's a measure that also machine learners know very well because it's used almost ubiquitously there. So very easy, of course, you square the difference between the model forecast and the observations and divide that by the total number of events. What is new for weather forecasting is then the definition of a skill score. And the skill score basically tells you what kind of improvement do you get from your model. And the idea here is that you relate the model to a reference forecast, and you also take into account a perfect forecast. So, for example, I mean, you can do that for any kind of score being some statistical property like the MSE. So the idea is that you basically subtract the reference forecast from your actual forecast, and divide that by the difference between a perfect forecast and the reference forecast. And then if, like in the case of the MSE, a perfect forecast would mean exact agreement between model and observations, which means that the MSE is 0. And then you end up basically with having the skill score being 1 minus your model forecast divided by the reference forecast. And so you can see that if you're, it basically takes into account that typically models of the atmosphere are not perfect. And you kind of measure then this, the improvement that your new model gives compared to a reference. So if your model has a smaller error than the reference model, you will see that you're subtracting only a little bit. So you will have a skill score close to 1. If your model is actually worse than the reference forecast, you will actually subtract more than 1. So you can actually get to a negative skill score. Now, typical competitor models or reference forecasts that are used in metrology are persistence, which means that you're just using the last known value and repeat it. And in fact, that may sound very naive, but in reality, if you look at it, if, for example, you have a temperature measurement at noon, it will say 26 degrees Celsius, then you can be reasonably sure that the temperature at 1 o'clock will not be that much different from 26 degrees Celsius. So therefore, persistence is actually a very strong model for making these short-term forecasts of the atmosphere. If you go towards longer forecasts, then climatology becomes a stronger competitor. And here we typically differentiate between monthly climatologies, which would be something like the mean of all January values, February values, and so on. So you basically construct a seasonal cycle with a relative monthly means. Or if you're interested in the journal cycle, you will have a journal climatology. So mean of all the 0-hour values, 1-hour values, and so on. And of course, you can combine that. So you can have a journal monthly climatology, for example, for January or for July or whatever. And here's one example how this can look like then as a skill score. So this is from a paper written in my group on ozone forecasting. And so we see the neural network forecast versus a persistence forecast. And we see that this is 4 days of forecasting. So the persistence, so that the neural network improves over persistence in all 4 days. But it's only, let's say, 20-some% on the first day, but it becomes a bit stronger in the following days. And that's just what I said. I mean, the persistence loses its value within a few days, whereas then the model approaches climatology. And this is shown on the right bar, right side, where you see the neural network versus the monthly climatology. And here you can see that in contrary to the persistence one, now the score, so the model is much better than climatology on the first day, but then it degrades. And in fact, it's a bit hard to see, but here's a 0 line. So it actually crosses the 0 line after about 3 days, which means that it basically becomes meaningless. So you better use a climatology than a neural network for days 3 and 4. And that's something that's actually not very common in machine learning, to use this kind of concept of a skill score, so to really evaluate your model quality. And so you will find many papers that just evaluate RMSE and then praise about how great their model is. But if you look at in more detail and make a careful evaluation, you will find it's actually nonsense. So that's something that you should be aware if you really want to get into machine learning for weather and climate. One other aspect, this is under the heading of a double penalty problem. Verifying cloud forecasts or also precipitation forecasts is actually even more difficult than verifying, let's say, simple variables like temperature or wind or so. And that's because of the so-called double penalty problem. So here is an example where they show a synthetic satellite image generated by a model. then an observed satellite image, and then you see the difference. And typically what you find in these different plots are these sort of bipolar structures. So just visually, the two figures on the left look reasonably similar. So you would say it's actually a pretty good model simulation. But if you evaluate it, you will find pretty gross errors.
So just a second. So this synthetic satellite image, it's from the machine learning or the deterministic model?
No, this is from a deterministic model.
Okay.
Yeah.
It looks really, to me, it looks almost the same. It's amazing. And how that's the forecast, like a couple of day forecast, or
I forgot what exactly it is, whether it's a couple of hours or days, I don't know, but yeah.
because eventually it just diverges, right, after some time, and then it's important.
Yeah. Yeah. I mean, ECMWF has a couple of nice examples on their webpage, how also how these sort of synthetic images improved over time. It's really mind-boggling, I think, what you can do with a model these days. But still, if you look in detail and you're an expert, you will identify certain things like the subtropical cloud systems that still look different between the model and the satellite images. But you have to look hard. Okay, and now what's behind this is the so-called double penalty problem, which means that even if you have a feature that looks very good, like shown on the left, so the shape of the feature is perfect, but it's slightly dislocated. Or you can have another error, which means that the forecast is just broader than the observations. And then, of course, in a good example, the two overlap. So there's hardly any difference. And the point is that you basically get a double penalty in evaluating these kind of forecasts because A, you're penalized for not having a pattern where it should be. So if you evaluate an RMSE, for example, taking the difference between model and observations, it will show you a large difference when the observations show a pattern, but the model doesn't. And yet you will get another big difference by having a pattern where it should not be. And so that's a so-called double penalty problem that one again should be aware of. And there are some methods now to deal with that. So certain statistics that people apply, or also object-based analysis, that you don't look at this sort of on a pixel by pixel basis, but you could try to delineate the shape of, for example, cloud patterns or precipitation patterns, and then evaluate them, for example, in terms of the stretch or the orientation of the shape and these kind of things. But that's still actually ongoing research. Right, another one that's also then useful and actually used fairly heavily in meteorology is the anomaly correlation coefficient. So this is basically like a normal correlation coefficient, but referring to spatial patterns. And it basically evaluates the structure of a forecast field. So whether you match the structure of a field. And a good example, we'll come back to that in part 4 of the lecture, when we look at some real examples of machine learning and metrology, is that, and if you use, for example, image processing technologies or machine learning models and let them do weather forecasting, you will find very good RMSE, so very good mean square errors on the fields, but they look very blurry. So if you just look visually at the results, you will find that should be a good forecast. It never. Because it's not meaningful, basically, because you cannot distinguish the different weather patterns. But still, on the mean, they're very good. And then in order to really, let's say, get a quantitative measure of that, you can use this anomaly correlation coefficient, and then you will see that indeed these machine learning models will do fairly bad. Okay, lastly, autocorrelation. Oh, sorry, this is just an example for ACC. In fact, I need to, okay, this is a bit from ECMWF again, where they basically just show the correlation coefficient, anomaly correlation coefficient, how it improved over time with their forecasting system. So from 1998 to 2022. And what's shown on the left axis is basically lead time until or as long as the anomaly correlation reaches 80%. So you can see that in 1998, this was about 5 days, and now they've come up to 6.5, almost 7 days. You can also still see a seasonal cycle, which is kind of interesting that, I mean, even though weather models are really good already, you can still see that, yeah, there are some things that people don't really have in their systems. Yeah, so there's some systematic deviation of the errors here. Okay, now final aspect is autocorrelation. You might have all heard about that, what that is in principle. So we could go into theory and start talking about Markov processes and stuff like that. Let's keep it simple. So the general idea is that we're coming back to independence of events. So that basically, if you have observed something at here in this case, it's days, at day 0, that there's a certain probability that you will observe the same thing again on the next day, or in other words, the observation of the next day is influenced by what happened before. And this can basically be described then with a so-called AR1 model, so autoregression model of order 1. And you basically see then that the subtracting the mean value of the observation of the next time step, you will find this kind of correlation factor here, phi, and then some random error on top of that. Right, and so in this example here, that's the maximum temperatures in Ithaca in the US, 1987, but you can see that this process, basically temperature changes have a lag time of about 5 to 6 days. And so that's a typical time scale for kind of weather systems. Yeah, so that's, for example, if you have like a high pressure system, it will live for roughly 4 or 5 days before it will be replaced by some other weather system. And so that's what you can kind of see from this kind of autocorrelation plot. Now, this has important consequences for how we do machine learning. And that's because whenever you start looking at machine learning courses, reading books about machine learning, one of the first things you will hear is that to prepare your test validation and training data sets, you will do random sampling of your data. Well, if you do random sampling on autocorrelated data, you get a bias. You will become over-optimistic in terms of your forecast, because your training samples and your test samples will be taken from the same data, basically. So it's much easier then for the machine learning model to get it right than it should be. And this leads to basically the requirement to be aware of your sampling technique. We've sort of pondered about this a little bit in our group. So this was really one of the first things we came up with when we started. So on the top, you see this kind of typical random sampling approach. You would just sort of take individual samples all across the time series, and in a, let's say, typical classical machine learning application, that's a good way to proceed. It's not in metrology, but rather you want to preserve basically blocks of a length that are much longer than this autocorrelation timescale in order to avoid these biases. And so there are different strategies you can take. For example, you could just do sequential sampling and just have the training set at the beginning and then have a validation and the test set at the end of your time series. Or you can have some sort of block sampling, taking out, for example, individual years that you put aside for the validation and testing. Or you can do a block sampling over a couple of months so that it's scattered across the years. And then ideally, of course, what you would do is sort of build an ensemble of your data set so that you get different of these samples basically and run the model a couple of times to evaluate the error. And this almost brings me to an end, which is a summary that we put together in a paper in Filtrans about sort of the typical peculiarities of atmospheric data that can make your life difficult as a machine learner. So there are things like having many different processes that determine the future evolution of the atmosphere rather than a well-defined physical process that drives things. For example, if you want to learn a pendulum or something like this, it's relatively easy in comparison. Then you have this coupling across a wide range of spatial temporal scales. So I did show you the different time scales and length scales in the atmosphere. What I didn't mention explicitly is that they're all coupled together. So many small eddies can cause a large weather system, for example, this famous butterfly effect. Then in terms of observation data, you have missing and erroneous values that you have to deal with. You have non-Gaussian probability density functions, you have periodicity, that's another aspect of data that machine learning systems generally don't like. You have the dynamic correlation, so they can change with time. So for example, correlation between an air pollution variable like ozone and temperature changes during the seasons. You can have you have the autocorrelation of time series that matters. You often have also imbalanced data, so in particular the scarcity of extreme events. So if you want to do, for example, precipitation forecasting, this is really a tough topic. And finally, there's a very strong need in comparison to many other things. I mean, if you generate images, for example, they just shouldn't look nice, but in meteorology, it's really important to know how good they are and to evaluate basically uncertainty of your forecast or interpolation or whatever. That ends part 2 in the first part. So we're breaking for coffee. Are there any questions before we leave for coffee? Ben.
If I didn't miss it, you saying that these field programs are rather useful for weather prediction. But isn't it generally useful for all kinds of machine learning models?
I think one could argue this, yeah. It's just a concept that's not widely applied outside of meteorology. Yeah.
Okay.
Yeah.
In your article, you focus like on deep learning. So I mean, there's algorithm specific neural net-based algorithms, you know. But I think you wanted to say machine learning in general.
In principle, yes, but the focus was a bit on let's say most modern types of machine learning technologies, and this is partly related to the fact that we just have a sheer amount of data here. So you have like petabytes of meteorological data to work with, where yeah, you basically want to have complex models to really digest them. Yeah.
And when you look at other fields, I mean, so not climate science, but the people who do deep learning application stuff, they do find that you can simplify things, you know, without explaining mathematical everything structures. Even I think they did some models to explain universe or something. I think yeah, so it's that because there are some structures that are actually very simple, but we don't see them because, like in the crystals and stuff, crystals are some simple, you know, principles, and then you have these shapes that look super complex, but behind it is actually simple algorithms, and these can be then, of course, matched with machine learning.
Okay, well, I guess we'll come back to that in the second part. In a way, so okay. Remember that question. If I don't answer it in parts 3 or 4, then ask me again. But just in a nutshell, I think what I try to show you with these few differential equations that I showed you, like the momentum equation, I mean, we do have a pretty good understanding of what's happening in principle in the atmosphere. The problem is that, I mean, due to, for example, all the complexity of the orography and all kinds of other factors, these equations don't really capture every detail. And it's really scale dependent, and then we'll get back to that.
You color these two puzzles. You color them.
That's just for optical reasons. So there's no.
You have to pick up what's the most challenging. What do you think? What's what the science will suffer the? It has to put the level.
Well, I guess the point is really the combination of these things, and that's kind of why we selected this jigsaw as a way of displaying that, and that's because in machine learning, if you look at it, all of these individual aspects are being dealt with. Yeah, so you will find papers dealing with imbalance, you will find papers dealing with dynamic correlations and so on, but typically it's only that aspect. And in meteorology, we really have to put them all together, and that's kind of the system that doesn't exist yet. Yeah.
Okay, let's stop for the coffee break. Come back. We start the time. You see now everything starts exactly on time because there's people online. So please come back. We continue.
Thank you.
down a bit
Mhm,
because
yeah.
it's pretty warm.
Yeah.
Then we have to reconnect you again.
Okay, it's good. Very interesting. Yeah, I published some paper. They cited now a lot. You know, geostatistics. You know, kriging.
Yeah. Yeah.
So they develop all the formulas and stuff. So I just geographical distances, but I stack different types of distances.